Okay, and we should be live now for the 2014 AP Calculus FRQ run through. Let me just run this through real quick and then we'll get underway. Okay, and then let's just make sure we are good on that. Okay, so a couple updates, of course, is that any emails being sent to the one down in the bottom left side of that screen there, and we will be going over together if anyone has any problems, either AP Calculus related or below. But as of right now, we'll be going through the 2014 free response questions of the AP Calculus AB old exam through all the free response questions. Again, a good way to practice is to make sure that we know how to answer the types of problems which they've asked before. Overall, and through my experience of teaching this through a number of years, is there really is no difference for the amount of problems or the type of problems that are being asked. Mostly, just about all of them are going to be fair game for this year's exam questions. So, as always, I'll have this off to the side. Don't exactly have all of the means to show both on the screen at the time, but again, all these questions I'll be written down in some fashion on my notebook, and then we will be going through them one at a time to make sure that we are ensuring that we are together going through each individual problem and then seeing how that will look like. Okay, so again, as before, we'll be going through 2 problems at a time here, and then we can truly begin. So let's go ahead and hit the music button here. Make sure we have that all there. Okay, let's make sure we're tweaking some settings there. Okay, very good. Then I think we are good to go. And so with that, we'll go and see how we can start answering these questions. Alright, so let's begin. Questions 1 and 2 are going to be calculator allowed, so I'll be showing this as well. The screen of my lovely and durable TI-83 Plus when we get to the parts where there's going to be problems answered by the calculator. But again, as something of my own philosophy and a YouTube short that I've made, is that the calculators are only really meant to be used at the very end of our work here to ensure that we're not using it as a crutch, but as a tool for us to get our answers from. Alright, so let's begin with this session, shall we? Let me just title this. Okay, so let's begin with question 1. Hopefully that can be very easily seen here. Okay, so we have grass clippings here, very apparently applicable. Okay, and they're going to decompose. Alright, so we're going from 0 to t to 30. Okay, and then the remaining function is noted as a of t is equal to 6.687 times 0.931 raised to the t power. Our a of t is measured in pounds, and then t is in days. Okay, that is the context of the problem. And so let's have a look here as to what problem A is asking for us to do. It says here to find the average rate of change of A of t over the interval 0 to t to 30. Okay, and then indicate units of measure. Alright, Very good. And so with that, we should be able to go and start putting some things together here. All right. So if they're going to ask us about the average rate of change for this type of problem, well, we're going to go ahead and need to list down exactly that equation. So average rate of change, of course, is going to be listed with our function at our ending point minus the function at the starting point of 0, all raised over the change in that value. Okay, should be fairly simple for us to follow along with. So let's have a look here what that looks like. Okay, so a of 30 and a of 0, so we can plug that right into this equation before we go and fit that into our calculators here. So 6.687 multiplied by 0.931 raised to the 30th power minus 6.687 multiplied by 0.931 raised to the 0th power over 30. Okay, to save ourselves some time before we start typing in a bunch of numbers right into the calculator, this guy goes back to 1 in that sense. Okay, and so we should be able to then input that into the calculator. So let's see if you'll be able to see. Maybe I should adjust the lighting here on this. Maybe the shadows are a bit too harsh on that, but I'll be tilting it upwards, I guess, to show a bit like this easier. Okay, so that's going to be the 6.87 multiplied by 0.931 raised to 30th power subtracted by 6.687, and then from there we need to divide everything by the 30. There you go. So you end up with -0.961 if you're going to go to the fourth with rounding that. So -0.1961. Okay. The units of measure now again is that these were the pounds on the numerator, and then we're dividing it by the days in the denominator. So that'll be pounds per day that are being removed from the bin. Okay, very good. So we'll hold off on the calculator until we need it next. And let's have a look here at the next problem. So find the value of a prime of 15. Okay, and it says here using correct units. Interpret the meaning of the value in context of the problem. Okay, so with that, we can go ahead and take a look to see what that really looks like in forms of what this function will look like. So on this sense though, we're going to have, actually just 1 second, so let me make sure I change this properly here. Okay. All right. So we have this now. They're asking for the derivative of the function of a of 15. So let's see what that looks like on this sense here. So we're gonna have to need to go and take the a prime of t, but because it's a calculus section, we can actually plug that in ourselves. There should be a way to do that. And then the thing is though, the second part of the problem is to actually make that in the context of the problem as part of the answer. So what our calculator allows us to do is that, at least for me, using the math button, we can go all the way down to option number 8 for me, which is going to be the function derivative option. So we can take the derivative of a function, and that function in our case is going to be the 6.687 multiplied by all of 0.931 and then raised to the and our case would be t, so we can put that in as a letter there, raised to t. Okay, so all of this is going to be in reference to the variable t. If I can remember why I just put that. There you go. And then one value that we're going to record it for is for 15. Okay, and there you go. We end up with an actual result of negative 0.1635. Okay, and so with that, we will then actually get a result from our calculator here. So negative 0.1636, rounding it. Again, that's still going to be pounds per day as well as the units. Okay, so pretty straightforward for what we're doing on that sense. And so we'll be able to put them together here. Now we have to describe what the context of that problem will be like for this. Okay, and so because it's asking for the context here, again, the units resulted in pounds per day. Again, that is the pounds of grass decomposing at the 15th day. So remember that this would be the rate of as well, right? We're measuring in pounds per day. That's going to be the rate because there's a time factor below there. Okay, that will then show what that looks like in terms of being able to describe to us how much grass is being removed from the bin on each of those days. Okay, so let's make sure I have that box there. So those are the two things that we really need to point out for this problem for us to get full points on that section. Okay, part C, find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the interval 0 to 30. Okay, so because of that, let's have a look here. We're going to see how the amount of grass is going to is equal to the actual average amount of grass, over the interval. Okay, so they're asking for two things here. Again, the average amount of grass and then the actual time t for that. Okay, so an average amount of grass, though, that's going to be average value, which will include a little bit of understanding on the fundamental theorem of calculus. But then we need to find a time that matches, which most likely means we're going to have to graph that. Okay, so let's see what this looks like here. So average amount of grass. Okay, that right there is going to be determined with the average value equation, which is going to be 1 over 30 minus 0, so the interval there. And then we take the integral of the actual amount of grass here that is inside of the container from 0 to 30 of the a function 6.687 multiplied by 0.931 raised to the t power dt. Okay, so this can all go inside of our calculator and it will give us an actual numerical value. So in the same manner, we can go and bring out our calculator to run this really quickly through. Okay, so for me, it's going to be the math button, option number 9 for an integral of a function. So we're going to plug that in. So 6.687 multiplied by all of 0.931 raised to the t power. Okay, and we're integrating this for the for the variable t from 0 to 30. Okay, so again, you gotta remember how to do the syntax properly on your calculators, but this is really what it's like for this one that I have. So by running it, we end up with a value of 82.579. Okay, so let's see what that looks like. 82.579. Okay, so because this is the average value of the function a of t, it's still going to use a of t units, that is, for that result. So this is still pounds. Again, this is the average amount of pounds that are in the bin from the 0 to 30 days. Okay, I'm gonna have to keep that in mind as we move along here. Okay, but they're not done yet though. They want to find the t. Again, the second part is find the time t in which the actual function is gonna match that value, 82.579. Okay, with some good old intermediate value theorem, if we remember that from the beginning of the course, is that we can guarantee that the 82.579 pounds is guaranteed to have been crossed by a continuous and differentiable function, which is this function indeed. Okay, so what we're going to have to do then is that we're going to have to go run through some different types of functions here, and so we should make sure that it's equal to 0. But the idea is that we do need to set it to 0, so that's easier for us, our calculators, to zero in on that result without much of an issue. So let's have a look here. So again, we want the 6.687 multiplied by 0.931 raised to t power to be equal to the 82.579. Okay, so in order for us to put this in the calculator, is a lot easier, is that we would have to subtract that 82.579 to the other side, such that we can then isolate the function on its own to be 6.687 multiplied by 0.931 raised to the t power minus 82.579. And so with that, we will then confirm here that we are dealing with just a 0 that the function can look for once you put it inside of the graph. Okay, so that way all we're looking for is a crossing of an axis, such that we can then just have the calculator tell us exactly where that is for the variable of t. So I'm going to start doing that here on the calculator, and so that way we can both see what that looks like. So clearing out what I did last time, let's begin to do that. So it's going to be 6.687 multiplied by 0.931 all raised to the x power. Make sure I have to do x now because we're dealing this in a graph. That's the only way this graph knows how to deal with that. And then we subtract the, it was the 82.579. Okay, so that results in that equation first. Okay, and let's see here. So only going from 0 to 30, we need to make sure we set our window here to make sure that we need to go up to 30. And then the y's, I guess we can go up to, like, let's say 90. Well, not negative 90. Let's do 0.5 should be fine, but 90 at the maximum at least should show us what we need right now. We'll get a nice look at the curve here. I do believe, oh yes, actually because it's so close, we subtracted, we actually don't need that curve. So let's change that again. We don't need 90, we're just going to need, let's say, 1. I think that should be a lot easier. That's a little bit odd why that's not showing. Let's take a look at the table then, shall we? Let's see here. Table form of this. They're all negatives are gonna reach to 0. Or are they not? Very odd. I think maybe it's because of the way that I wrote this, but I wouldn't think so either. Let's have a quick look here, why don't we? Let me go ahead and really quickly make sure that we're on the right track here. insert that in there. Okay. Is there any change to that? Oh. What is up with the syntax? I don't see a problem here. Oh, I did use the wrong. Okay. I doubt that parentheses will make a difference. This calculator should know what it's doing with that. Yeah, okay. Then why don't we go and take a quick look back at what was given to us before. So let me see if I can do that really quick for you, just to make sure we're starting on the right spot here. That it's the 6.687 0.931 raised to the t power as we stated before. Okay, and then we're just taking this for the variable of t from 0 to 30. The average value still holds up. Okay, so again, the subtracting it should have been the main idea, to be able to get that to match onto the average value. So let's check one last time back to the graph here. That 687,931 raised to the x power for that. Okay, so let's just have a look here. If we didn't do that, the subtraction, 6.687 multiplied by the 0.931 raised to the x power. Okay, we'd end up with the graph. My window's a little bit off, so I want to take a look at the table once it's done iterating this. Okay. Okay, we get close to 0, looks like. Do that anyways, without the help of that. Oh, I know exactly why. Wow, it looks like I made a mistake, which I need to make sure that we didn't do. It's because with that 82.579, we did not go and divide the 30, which was there. Wow, and very interesting for me to make that kind of mistake, but we managed to catch that before we went too far. So let's divide that by 30 as what we need to do, and we actually did end up with the correct size that we do need here of the 2.753. That is the actual average value of the function. So let's take it from back here and make sure we divide it by 30. So from this mark here, we should be able to note that it's going to be 2.573 pounds is the average amount of value that is inside the bin during the entire time from 0 to 30. And then from there, we'll be able to then redo this part of it. So let's change that then. Let me strike that out to make sure we're doing this properly. So it'll be subtracted by 2.573 is equal to 0. So this is now the true equation of the graph that needs to be inputted into our calculator, such that we will be able to determine what is needed in our problem here. So let me just quickly run through this really fast. There you go. Okay, and so let's put that now into our calculators here. So we're now subtracting just a much smaller number, 2.573. Okay, so if we were to graph that, that will look a lot easier for us. Looks like, there you go, we have a nice even cross through the axis for us to reach a 0, in which that will be the resulting x value that we're looking for the whole time. So let's go and trace a 0 for this actual graph here. So we're going to need to go to the left side of that crossing, and let's go to the right side of that crossing, and it's going to calculate that for us. It ends up at 13.359 if you rounded it. Okay, so t is equal to 13.359 days. Again, that's when the y is equal to 0 for us. Okay, so this is where that's going to be. Again, this is where we're at the 2.35 days. Our function a is equal to that value that they wanted, the average amount. That was the 2.573 pounds average that was across the entire 30-day span for this problem. Okay, so those are the two parts that they were looking for, which took us a little bit longer, but with our perseverance, we managed to get through it just fine without any other issue. Okay. Very good. Glad we were able to get through that without a problem. We'll see what the grade looks like once we're finished with the second problem. But let's go onwards to the part D, and then that should conclude problem number 1 for us. So let's have a look here at part D. It says here for t being over 30 days. Okay. L of t is a linear approximation at t equals 30. Okay. As a better model for the grass in the bin. Okay. So it says here use L of t to predict the time at which there will be 0.5 pounds of grass left in the bin. Okay, very good. So with that, we would be able to then go ahead and take a look to see what that looks like, at least for us. Okay, so it says here, for those that are confused that why isn't there an equation for us, it's because L of t is a linear approximation. That's something that we should be able to do ourselves for this type of problem. Okay, and they give us that exactly at t equals 30. So again, linear approximation means that we're going to need the linear equation y equals mx plus b. Okay, where m is going to be the a prime of 30, right? Again, at the exact point which they told us at 30 days. Okay, so along with that, we will then be able to go and see to it what we can offer for ourselves from that approximation. Okay, so we'll take a look at this to realize that first we need to go take the derivative at 30, and then we need to find the actual intercept for that equation as well. Okay, which means we also need to find a of 30 as well to know the coordinates in which we can then determine where the intercept is to finish off our equation. So first things first, a prime of 30, we've done something very similar, where we've done a prime of 15 directly into the calculator back in problem B. So in a similar fashion, we just need to do a prime of 30 for this current problem. So as shown from the calculator here, there is, at least for me, a function to be able to plug in for a derivative of a function. Option number 8 for me. If it will do that, okay. I kind of pressed enter too much, but so we have that for option number 8. So the function goes right in there, 6.687 multiplied by 0.931 raised to the raised to the t power for the variable of t at 30. Okay, and let's see here. I did not close the parentheses because that's hilarious. There you go. So that way we have that also. There you go. Okay, so without any other issues here, it's negative 0.56, just going to the decimal places, so negative 0.056. Okay, and I wrote that in the wrong spot because I'm just so good at this. Again, that's the pounds per day, and then a of 30 now. Okay, so as seen here, again, we have both the a prime of 30, which was the slope of this equation that we're going to make, and now we need the actual y value, a of 30. So that's a very simple plug and play here. 6.687 multiplied by 0.0931 raised to the 30th power. Okay, and it turns out to be an extraordinarily small number. Okay, that's going to be 7.829. Yeah, it's 829 times 10 to the negative 31 power. So that is so extraordinarily small that we can more or less approximate that to 0. Again, that E31 there is leading with 31 zeros past the decimal point. So far too small for us to really make any difference on. So with that, we can then go ahead and plug this in. So that's y is equal to that slope of the negative 0.056 multiplied by x. The result here is that because if we plugged in for 30 here, right, so at 30, let me double check this, because at 30 it's going to be, yeah, so at y is equal to negative 0.056, and at 30 days it is practically already 0 for us at that point. So with the plus b that's remaining, so we still have the plus b we have not solved for, the b will be equal to that multiplication, so 0.056 times 30, which is negative 1.68 added to the other side. Okay, so just to show that we're doing this in each stepwise, again, that's going to be y is equal to negative 1.68 plus b, which is equal to 0. And then by adding to the side, b is equal to 1.68 positive that way. Okay, so with that, we actually have our final equation here. Y is equal to negative 0.056 times x plus 1.68. And now it says we need to find it where we get 0.5 pounds of grass remaining in the bin. Okay, so if we want to set that, 0.5 is equal to negative 0.056x plus 1.68. At least for me, I'm not looking to take any chances during the calculator section, so we just got to move this over and we can graph this in order to find exactly what we need. So with 0 being equal to negative 0.056 6 plus 1.18, which is the result of that subtraction. And we need the x there. I don't know why I didn't write that. Okay, so our x that we're going to be able to find from that sort of calculation there. Let's have a look here. So with that new graph here, it's a negative 0.056 multiplied by x, and then adding 1.18. Okay. So I think our window needs to be set. Let's change that from the third. Let's change that to, because we're starting at 30 already. So you go from 30 all the way to maybe, let's say, 50. And let's take a look at that graph. Okay, it looks like it's a bit too small for us. Yeah, we already crossed into the negatives at exactly 30, which is a bit odd. Oh, we need to go a little bit below that. Okay. Yeah, okay. So let's change that table, the window here. Let's go from 0 to 30 then. Okay. There you go. Alright, so let's calculate a 0. That can be a lot easier to see now from here. So we're going to guess from the left to right side here from this. So left bound, and then we go right bound there. Okay. And then x is equal to 21.071. Okay. Alright. Looks pretty okay on that sense. But let's double check for this here. Linear approximation at t equals 30, because we did plug in for 30 there. 30 at the exponent is be quite large here. Yeah, that was the case. Okay. And taking it down to 30 was exactly 0. Okay. Yeah. All right. Yeah, I think we're pretty good on that. So, let's see here. trying to see what they're trying to exactly say about this, because our t is a little bit less than 30, which is not exactly the case in which it should be for this. And a prime of 30 was correct, right? Yeah, that's still a correct 0.056. Alright, we might need to go back to this at a later time, but as of right now, we'll leave it at the 21 days. Doesn't seem like it should be. I'm not too confident in that answer for now, but I think we'll be the better for it if we took a look back to get a better understanding for that. Because other than that, let me double. My curiosity has been piqued. I want to double check something here. So 0.687.931 raised to the x power. Oh, so we don't reach that at that point. Wait, then what do we reach? What? Oh, no, we do. But why is 30... What is happening here? Hang on, sorry. Something is not right. It's because I did that incorrectly. Okay. Let's go back here. Okay. I realized there is an actual mistake in my work here. So I accidentally put in 0.0931 where it shouldn't have. A very small mistake for us because that resulted in me putting 0 into the equation. So it's 0.783 is the actual correct sizing that we should have for this. So because of that, we're gonna need, so let's start all the way back here. So it's the negative 1.68 is not equal, plus b is not equal to 0 right now. It's the 0.783 right there. Okay, so we're gonna have to change that up here. So b is not equal to 1.68. b is gonna be a little bit larger than that, into 2.463 instead. Okay, that is the actual y-intercept of b. So with that, we're gonna have a different result here that we're gonna put, instead of the 21 days, the 0 is equal to negative 0.056x, and then we're going to subtract the 0.5 from that, so plus 1.96 instead. So because of this, we're going to end up with the actual correct x value for ourselves here. So let's have a look on that. That's going to be negative 0.056 multiplied by x, and we're going to add that with 1.96. Uh, 963, yeah. Let's put a 3 as a third decimal place. Okay. So let's see if we put this right in the screen here. So negative 0.056 multiplied by x, and then we're going to add that with 1.963. Okay, so this is the actual function that we want to find the new 0 for. Okay, we put that into the graph, we should get a nice scroll through there. That should be beyond. That should be indeed beyond 30 because that's what we're looking for. So let's change the window here to take us from, let's say, from 25 up to 50. There you go. That's a lot better. That's something that we can be able to calculate, which is beyond 30, which is what we wanted in the first place. So looking for a 0 here. We're going to go left side of that, right side of that. And it gives us 35.053. Well, 54 if we already did round it properly. So 35.054 days. That's how long it takes for us to get the 0.5 pounds as requested left in the bin using that new form of being able to approximate where that new function is going to be. Alright, that took a little bit longer than expected, but we're all still the better for it to show exactly all the steps we need to do to make sure we get a sensical answer for us in order to reach something that we actually want to work with. Very good. Okay, so we'll come back to grading all of that once we're done with problem 2. So let's get on with that. As a reminder, again, you can email me directly or go to the chat for any of your problems you'd like answered. And because this is just something that we're going over through together on this live stream, your questions actually do take priority on this rather than what I'm doing right now. But nonetheless, since I haven't got anything yet in my feed, we can go over the actual problems together. So from that, let's have a look here. So problem number 2, we have a lovely graph here. Make it quite deep here. So we have one straight line coming across, and then we have a function coming around and then down underneath here, and we'll call that R. Okay, so X and Y. Okay, so it says here, let R be, make sure we have that be the region enclosed by the graph of f of x is equal to x to the 4th minus 2.3x to the 3rd plus 4. Okay, and the horizontal line y is equal to 4 as shown in the figure above. Okay, so we have that all sorted out for us. Okay, and then so let's see what problem A is asking for us here. It says here, find the volume of the solid generated when R is rotated about the horizontal line, y is equal to -2. All right, very good. So we have the setting here in which we're going to do a bit of rotation. All right, making a 3-dimensional shape from a 2-dimensional graph with some good old rotation. Okay, so something we might need to know here is that we need to know these actual points of intersection to know where we're going to start and finish this integral in the first place. Okay, so thankfully, because we know this is y is equal to 4 as a line that's coming straight across, it should be pretty simple, where it should be 2 points in which this graph crosses the y equals 4 line. So again, so f of x is equal to 4, and that's equal to the x to the 4th minus 2x cubed plus 4. We really are just looking for the points where, if it crosses 0, for the remainder of the function of x to the 4th minus 2x to the 3rd power. Okay, pretty nice for us, because then our calculator will spit out that the x values, at least for most of our cases, will be the limits of our integration. So let's go ahead and put this right into our calculator here. That it was x to the 4th minus, and this is 2x to the 3rd. Okay, so because of we have that, that should be good enough to take a look at. Our window's a little bit messed up right now, so let's make sure we go from 0 all the, let's say, to like 10. So let's graph that. Let's have a look here. Not 10. I think it's because a little bit more than 10. So let's change our window a little bit below that. So -1. And then let's have our y going from -5 to +5. That's a little bit more like it. Okay. So let's go ahead and trace that for ourselves to know where those zeros are. It looks like we have 2 there. Let's go all the way back towards 0. So we're left of 0 and then right of 0. This should be exactly at 0, right? Because that should be already. I think I made the calculator a little bit angry with that kind of a question, but it still should be able to, at least for us, it should be noted that 0 is quite an obvious answer for us here. So x being equal to 0 is going to be one of them. And then the other one, though, that's the more important one, at least for us, is the next 0 that we're going to look for. Is going to be right below that side on the left, and then we're going to go one more to the right, and there we go. If x equal to 2, that is the other 0 for us to follow with. So again, these are going to be the limits of integration for us. Okay, but something that I then would like to note is that when we're looking to rotate around this y equals -2 line, again, that's going to be some line way down over here in which they're going to do the rotation around, okay, to generate that kind of a solid. And so with that, we do need to know what is we consider the big R, little r, right? So what is the actual radius that are going to be subtracted from each other while we integrate for this. So obviously we're looking for this solid here because that's the region R which was enclosed by the problem. And so it looks like for this problem, right, going from very top to the very bottom, okay, that is the y equals 4. That's the big R, so that's the larger radius of the two. And then the one that's dipping down there is going to be little r, right? That's the f of x, which is the little r in our case that will be subtracted away from it. Now, a common mistake here is that people are going to go, well, that's so simple then. We're just going to get the y is equal to 4 subtracted by f of x and then slam that into the integral and we are home free, but that is the clearest way to make the easiest mistakes on this type of problem. Okay? Because this integral, the way that is written out right here, the way people want to, is only the distance from the either function, so y equals 4, or the f of x function, only to the x-axis, right? That's what those integrals are really showing for that, okay? So we're having a little bit of an issue because we need to include a little bit more than that, than just the x-axis. We need to go 2 units below that, right? So what that looks like is that y of 4, if we were to take this integral now, from our 0 to 2 limits, is that y is equal to 4 is not just a 4 distance from the top to the axis. It needs to go all the way from that line all the way down to the dotted line, meaning that we need to then add 2 more to each of those values, right, going all the way across. The same will hold true for our little r here for f of x, which is going to be all of x to the 4th minus 2x to the 3rd plus 4. But because of that, we need to add 2 more to that value there, to ensure that we're adding in the extra 2 distance there to match that, okay? And then we can go dx. So now this is how we're going to integrate this this kind of problem here. Now thankfully, actually, we should be pretty okay for this because with this subtraction, we can actually cancel some things out, noting that the 4 plus 2 being subtracted from each other will both cancel out to 0. So all that we're really dealing with is an integral from 0 to 2 for negative x to the 4th plus 2x cubed dx. Okay. Now, I'm actually realizing there's a bit of an issue. Let's back up because I am also myself jumping the gun a little bit. It's going to be, the integral in this sense is going to be big R squared minus little r squared dx. Okay. All right. And so because of that, this rotation is going to be a little bit different instead of that. Okay, so it's going to be the actual squared versions of each of these, which is going to hold a lot different than what we're dealing with currently. So with that in mind, let's do that properly into our calculators, and let's see what we end up with. Okay, so let's go run the integral, this time of 6 squared subtracted by x to the fourth, let's see here, minus 2 x to the third plus 6, and all of this raised to second power for the value of x from 0 to 2. There you go. 17.6168, okay? 17.168, and because we're doing a rotation again, there's a pi waiting for us on the outside because we rotated this fully around in a circular motion. So by multiplying the pi and giving this a calculator section, we'll just need to make sure we throw that in there, at least for this. So that's going to be 553.936 as our total volume for that solid that we made. Okay. So again, a lot of steps in which we need to continue practice to make sure we know we're fully good on. Okay. Part B says here that region R is the base of a solid. Okay. For the solid, each cross section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Find the volume of the solid. Okay, so a little bit of a wackier problem given that we're now changing the shape of the solid. So as a little bit of a reminder in our own heads, think of again, if we had the shape of R down on the two-dimensional plane, we want isosceles right triangles peeking out of it, right, out onto the third dimension. And that's not exactly the best drawing, I would say, but nonetheless, though, the idea being that if we had a right triangle, R is going to be one of the legs again. It'll be R again on the vertical plane, but all we have right now is the actual shape of R in the function that we have like that. So then we need to integrate across that and then figure out what the volume is there. Okay, so before we do the integration, again, the area of a isosceles right triangle is what they showed there. It's quite simple. It's simply just going to be 1/2 r squared, given that. It's just simply going to be the actual squaring of a square, we're just cutting it in half, which is why that 1/2 coefficient is right there. Okay, so for our volume here, okay, we're going to need an actual integration here for this. Okay, so it's going to be 1/2 from 0 to 2. And this time, instead of that difference again, so it's rotated now again. So yeah, it's not rotated against anything. It's just the region itself being extended forth from the plane. And so because of that, our equation will not look like anything like this right now. It's just going to be the difference between the top and bottom of that region R. Okay, which in this case is going to be a positive 4 minus all of this now, the x to the fourth minus 2x to the third power plus 4. Okay, and because of that, this is R now, right? This is the region in which we want to have squared, right? We're not subtracting one from the other and then rotating. Is that we need to make sure we subtract it first and then square it to reach the area that we're looking for. Okay, so that's the way that this is supposed to look like. So because of that, we can run some very simple changes here before we run everything down. Is that's negative x to the fourth plus 2x to the third and then dx like this. Okay, so with that, this is a much easier volume to input into our calculators here. So if we go to the integration function once more, that it's going to be the negative x to the fourth power plus 2x to the third power. And then we're running this for the value of x from 0 to 2. Okay, and something to keep in mind here is that we're supposed to square all this. So let's see if I can quickly insert that in before we waste all of our time here. Let's insert that and then make sure that it's going to be squared. There you go. Okay, very good. And then we multiply a 1/2 on the outside of it, just waiting as a coefficient after the integration. Okay, so let's have a look. It didn't like what I did there because I put that in the wrong spot. Let's delete that. Make sure. Oh, no, I wasn't. This is still raised to the third power there, and then we have the parentheses taking us to the second power. Okay, there you go. All right. Yeah, that is a lot more like it for us. Very good. Okay, so our area is going to be 1.016. That is the volume for that instead. Quite a way smaller because we did a lot less sizing of this. We just went straight from the top to the bottom. So that looks pretty good to me for that. So we should be good on that sense. Okay, very nice. So let's go to part C here. The vertical line, x is equal to k, divides R into 2 regions with equal areas. Right? But do not solve. An equation involving integral expressions whose solution gives the value k. All right, very nice. Okay, so they're giving us almost a freebie here, I would say, because we're not actually going to solve for anything really right now. We are just going to give them an expression which matches what they're looking for, and we will be well on our way. So to look at this in an easier light here, so we have our axis here, that's our y is equal to 4 line, so that way we have our function, something like this. Okay, just to make it look easier. So because this, again, we have some vertical line, x is equal to k, in which both areas will be equal to each other. Okay? And so they want us to find a single equation, right, that will give that value of k. Okay? So then we need to find what each area looks like, and we'll go from there, right? So if k is going to be that line, again, this is going to be the true limit of integration for us that will stop it in between to make sure we're equal on both sides. For example, right, going from 0 to k for the area, right, and then that should be equal to going from k to 2, because 2 is the end of our other limit of integration, for that same area dx, right? That's what they're saying we need to look for. Now we're just going to make it look a little more professional, and we'll be well on our way, right? So going from 0 to k for our first bit of the area, right, it's going to be the same for both sides. It's just that we're looking at the same area of both sides. Now, the thing is, though, it looks like, I'm trying to see here, what that'll look like first. Okay, because we need to have this in such a way that it's literally just k isolated on its own. So let's have a look on this. So that's going to be the area function, which is going to be 4 minus all of x to the fourth minus 2x to the third plus 4 is equal to k to 2, the 4 minus x to the fourth minus 2x cubed plus 4. Okay, so we covered there. But when we fill that out, we still need to find a way to isolate for k here. All right, and I think we might be getting somewhere close here, because given that we are using fundamental theorem here, we can actually isolate this to a lot more simpler, because it's cutting it exactly in half. It's just going to be half of the area from each other. And so with that, what we could do is that understanding fundamental theorem is that we can then take the derivative respect to k on this side of the integral. And so that ends up, if we simplify that 4 there, is going to be negative x to the fourth plus 2x cubed dx. Okay. So by doing that, we would then end up with variables of k instead. 2k to the third. Okay. No plus 3 because we're not really in any use for that right now. Okay, because we then took the derivative of a definite integral. All right. And so from there, that will be equal to half of the value. Let me double check here. But they said they want equation involving integral expressions which the solution gives k. The wording is not exactly the best here, I wouldn't say. But I wonder if what we written beforehand was good enough for them. Because the integral expressions did involve k, and that is kind of what they wanted here. Okay, you know what? Let's go ahead and run with that for now, because they're not looking for anything else really in particular. Let's see here. Because we in ourselves didn't exactly find the area on our own either, until it really was much later. Okay. So let's see what that looks like. Most likely I have to go back over again, because I personally don't really like the wording very much on this, but I think we'll see if that really institutes for anything. All right, very good. So let me go ahead and swap things back over here, so we can begin grading this ourselves for these first two problems, and then we'll go to the next two after that. Okay. So let me swap over a different ink color here as well on my pen. Okay. So question 1 at negative 0.196 pounds per day. That's the right answer with the units. That's literally just 1 point there. So 1 out of 1. Okay. Then for part B, the negative 0.164 or 163. Yep, that's what I have. Pounds per day. Okay. And then the amount of grass. Yep. Decreasing at the rate at the pounds per day at 15 days. Yep, so both the answer of A prime 15 and the interpretation are good. So that's correct for me. 2 out of 2 points there. Okay, going to part C, 12.414 is a little bit odd here. Did I really divide that properly? Oh, that's the daytime, right? Oh, 13. Wow, okay. That's a little bit off here. I mean, they wanted to show that we did get the us showing that we have the integral, the average value expression. That's the one correct. But it looks like I'm quite a bit off from the actual days of that happening. Okay, so we're gonna have to go over that real quick. So that's a no-go. So this is only 1 out of 2. Okay, T not correct. We'll have a closer look at that again. And then for part D here, this got it because part D looks like I got correct with the right time and the right expression for L of T. Yep, so yeah, looking at L of T, yep, that's exactly what I had. I just called it Y in this case. but that all matches up, and then matching it to 0.5 that we wanted before as well. So it looks like all three with the 0.0534 days all down to the decimal are good. Okay, so out of the it's 4 points. Okay, they graded this last one out of 4. The LFT expression looks like it's 2 points to really show what that looks like for us. Okay, so out of the 9 points, looks like I only got 8 out of 9 on this page. Okay, we'll have to come back to that after we finish grading part 2. Question number 2, that is, and we'll take a look to see what we need to go over really quickly to make sure we aligned it properly. Okay, looks like there is something a bit odd with what happened with me here. 2.3. Wow, I made a lot of mistakes. It looks like I'm not going to get much of this correct because this is my own mistake of not realizing that's 2.3. I got to be more careful on that. I wrote down 2s on a lot of these. So it looks like we might need to actually go over them again because they're not going to get anywhere except, oh, it looks like for part C though. Yeah, I need to go part A and B again on the answers. But part C, them actually splitting it exactly like that at the 2.3 marks is actually going to be correct on this. Okay, so let's make sure we go over that again. Definitely is a little bit embarrassing to show that I made such a simple mistake of not putting that 0.3 in there when it was very clearly written. So let's try that one more time. But it looks like, at least for everything, the way everything was set up is good. And so if I really were to get the closest to this, it looks like I'll get like 1 out of 3 here, and then also like 1 out of 4 there. So not the best because we made one very simple mistake, but we'll be all the better for it when we quickly go over that once before we get to the next parts. So let's go ahead and let's see, do I have any space here without using any extra pages? Doesn't look like it. Okay, let's just go off to the next page to redo part 1C here. Okay, so let's redo question 1C first, and then we need to go back to question 2 because of my terrible mistake. So 1C. Okay, it says here, find the time T, or again, where the amount of grass in the bin are equal to the average. Let's see, let's settle down on that for just a second here. Let's swap to a different playlist. Okay. Are equal to the average value amount of grass from 0 to 30. Okay, so let's try to recreate that properly this time, showing that where again the average amount is the 1 over 30 minus 0 for the integral from 0 to 30 of a of t dt. That's the average. Again, that is the average value equation. So at least for us, simplified is going to be, and plugged in, so 0 to 30 of the integral from 0 to 30 of the 6.687 multiplied by 0.931 raised to the t power of dt. Okay, let's make sure I still am correct on that. They didn't exactly show that in the answer key there. So let's make sure we are taking the integral. If the camera can focus here, one of my favorites on autofocus cameras here. Okay, so that's gonna be the 6.687 multiplied by 0.931 raised to the t power. Okay, all of that for the variable t from 0 to 30. Okay, make sure we are dividing by 30 after the fact to actually get the average what they want. So 2.753. So 2.753 pounds is the average. Okay, And so we need to match this with the actual graph itself. So again, if a of t is d, so y is equal to that 2.753, want to match that with the function itself, 6.687 multiplied by 0.931 raised to the t power. Okay, again, we want to set it to 0 such that we can easily calculate for that in our calculator. Minus 2.753. Okay, our time again is going to be written out as, if we show this in the graph here, that is going to be 6.687 times all of 0.931 raised to the x value this time because it's in a graph. We're subtracting it by the 2.753. Okay, as shown right there. We're going to be, if I remember, it was around the range of 13. So let's set the window to around 15. Let's have a look at that. Okay. And we do get the cross of that, a little bit hard to see, very much on the right side, but should be still good enough to trace for that, for the 0 value. So let's go to the left side of that as we get closer here. Okay, so we go above 0 here, and then below 0. Huh. Still gives 12.41, which is not exactly what we're looking. Wait, no, 12.41 is correct. Yeah, that is the right one. So 12.413. Okay, that is indeed the correct value which the answer key was looking for. It's just a matter of what was happening in. Let me double check it. What was happening in my previous answer here, though? Because that is the correct way of doing it. For what we did here, maybe I didn't exactly put that into the graph properly, because that's the way that I set it up previously as well. But looks like we're having some issues. Well, fortunately, my calculator, I cleared all the data on it, so I don't exactly have a way of putting that all together here. So, in any case, though, this is indeed the correct way of answering 1C, so we're good on that. Okay, now let's go back to question 2, though, that really big one, in which we need to get back to understanding that we have the true function here. So again, y is equal to 4 is one of them, and the function is equal to x to the 4th minus 2.3 x to the 3rd plus 4. Okay, so again, the limits of integration, it's going to be still 0 for us. Okay, but again, if we really wanted to show that, we have to make sure we graph that properly of their connection here. So it's going to be x to the 4th. Why did my guy get rid of? Okay, all right, minus it's 2.3 x to the 3rd power. So that's what it really should be for that. Okay, and so let's go and reset the window here. Let's go up to only 5 this time. What? What? 2.3. Hello? Okay. There you go. Okay. So now we have the graph there properly, at least showing what that's going to look like here. So let's go and trace some zeros here. So left side and right side of that one is going to be 2.3 comma 0. So that is the second limit of integration. Okay. So our setups are going to be just about the same here, in that for the part A question here, that the volume that they're asking for is pi on the outside, going this time from 0 to 2.3. And so it's going to be, again, it's going to be big R squared minus little r squared dx for us. Okay. And remember, for part A was asking that we were now rotating on y is equal to -2. So because of that, we're going beneath the x-axis. So again, as a little bit of a refresher here, we have the y is equal 4 line up there. We had the function coming down like this, and that's the region of R. Okay, so that's 2.3 right there, and that's 0 right there. Again, they're asking to rotate about the y is equal to -2 function instead. Okay, meaning that we have to add, because normally the only distance would match up to the x-axis there, and we were supposed to actually extend it a bit further down to the y is equal to -2. So what that means for us is that for the function in the integral here, is that the big R squared, which is going to be the 4, we're going to have to add 2 to that, square it, and then minus all of the x to the 4th minus 2.3, x to the 3rd plus 4, adding 2 to that as well, squaring it, and doing it in that fashion, such that we will then be able to add that extra little bit to the y equals -2 line, and we end up with a fully rotated solid here. Okay? So because of that, we can then put that through the integral here, and we'll be well on our way. So let's go ahead and make sure we have our pi waiting on the outside. Let's throw in the function integration here of, let's see, a 6 squared, and then we're going to subtract that with all of the x to the 4th minus 2.3 x to the 3rd, and then adding the 6 to that, squaring all of that, and from there we're integrating for the value of x from 0 to 2.3, and there you go. We get 90.868 as the true volume of that solid, which does match up exactly with what we need, with what we were asking for before. Okay, and then part B now, that's the one where again, they were doing the cross section that's perpendicular. Again, that's R and R, the isosceles right triangle for this kind of guy. My setup was exactly correct at the volume, except just the limits of integration. Again, this is going to be the region of R. All that's, so basically it's area squared dx. Okay, so for us, that's gonna mean that we're gonna need all of the 4 minus all of the x to the 4th minus 2.3 x to the 3rd plus 4, all now raised to 2nd power dx. Okay, so that way, again, the setup was all the same. It's just the limits of integration a little bit different to make everything cleaned up a lot nicer for me. It's going to be negative x to the 4th plus 2.3 x to the 3rd, and then dx, and then all of this is squared. And then we need a 1/2. That's right, we need a 1/2 as a coefficient to make sure we're dealing with a half of a square. That's what the isosceles right triangle is in the first place, and then we'd be able to put that through. Okay, so with what we have here is that we will go here into the hello, what's happening? Okay, so 0.5 multiplied by, oh, that's right, that the function integration of all of negative x to the 4th plus 2.3 x to the 3rd. Okay, and then all of this though, so we need to make sure we have that inserted properly to the 2nd power, dealing with x from 0 to 2.3. Okay, so it's 3.574. Okay, and that should have been the correct form of that as well. Yep, that's correct. That is the correct volume for this solid there. And then lastly, part C, that one was correct for me at least, given that we were doing 0 to 2.3, 0.23, which was, we need to be split into the 0 to that value k for the function, the 4 minus x to the 4th minus 2.3 x to the 3rd plus 4. It's just the area that we're dealing with, and that's going to be equal to then going from k to 2.3 for the same exact function. Because, again, we were splitting this exactly in half. They wanted that equation set up there, just like this. And that's all that they really cared for. Okay, so this was the correct form of that. So that was all good. And there you go. We finished our corrections on that. Cool. quite a bit of a doozy for us just because there's some silly mistakes done on my end, but that should be a lesson for all of us to make sure that we are reading through the questions and all the parameters of the equations properly to make sure that doesn't happen ever again. All right. So let's have a look here. Okay. Again, as always, any of the questions that anyone else might have, just throw that right in the chat or email directly. We can definitely go over that together. But for now, we'll continue forth with our packet here. So we're dealing with question 3 on this segment here. So this is no calculator, so my calculator will be off and away. For the rest of these, for 3, 4, 5, and 6, there will be no calculator involved, and we should be able to go over them together with no issue at all. Okay, so we have now a graph here. Okay, so we have going from 1, 2, 3, 4, 5, negative 5, comma 2. Okay, and then 2, 3, 4, so 3, 4, down there, 3, comma 0, down to 1, 2, 3, 4, 5, 2, comma 0, and then 4, comma 1, 2, 3, 4. Okay, so we end up with something like this with a lot of line segments going around like that. Okay, there should be one straight line, that is. Okay, and we have the points as such: negative 5, comma 2, negative 3, comma 0, 0, comma 4, and then 2, comma 0, and then negative 4, positive 4, comma negative 4, like that. Okay, so we have the graph of f here, as shown there. Okay, and then 3 line segments and shown for above. So g then of x is going to be negative 3 2x f of t dt. Okay, so I have that as the context of the problem. So let's see what that looks like for this. So this here to find g of 3 for this problem here to start with. So with that, g of 3 will then be for us as in the place of x from negative 3 to positive 3 f of t dt. Okay, which means we then need to find the area underneath that entire graph from negative 3 all the way to positive 3, which would be up there. Okay, so you have this whole entire triangle that we're dealing with, as well as that little section underneath the x-axis. Pretty easy. So again, we have a positive triangle, and then we have a negative area of the second triangle. Triangle 2, at least in my case. Okay, so for the first triangle, we have the area determined by the base of going across 1, 2, 3, 4, 5. So 1/2 times the base times the height of 4. Okay, and then we also then have the subtraction of the smaller triangle, which is really just a 1 by 1 triangle here. Or no, it's not a 1 by 1, it's a 1 by 2 triangle because it takes 2 steps. Yeah, because it takes 2 steps. This is a 3, comma negative 2 to reach 4, comma negative 4 on the next point over. So that's going to be 1/2 times a base of 1 but a height of 2. So that's going to be 1/2 times 20, and then 1/2 times 2, which is going to be 10 minus 1, which is equal to 19 underneath the curve. Very nice. Okay. And then from there, part B says on what open interval contained in negative 5 to x to 4 is the graph of g both increasing and concave down. Okay, and then we need to give a reason for that. Okay, so a graph of g is increasing concave down. So what does that mean for us, though? We put that in simpler terms, in mathematical terms for us. That means if g prime of x is greater than 0, that's the increasing bit. And then also if the second derivative is less than 0, that is going to be the concave down. Some good old definition and terms of some early units in calculus, and we should be well on our way through that. So if the g prime of x is increasing, then we need to get that set up. So what exactly does g prime of x look like? Well, if we're going to take the derivative respect to x for what g was defined as, we have good old fundamental theorem to rely on. For those who might not remember here, is that before we take the derivative, the fundamental theorem means that we take the capital F of x minus capital F of negative 3, right? Now, please take note, of course, that this is literally just a number, right? That's a value within a new function. So if we took the derivative, that's literally just going to bring us back to F of x minus 0, right? That's what the first derivative of g looks like, okay? So we need that. So for g prime of x is greater than 0, we can do a good old number line analysis, although it already is there on the graph. We just want to make sure we can compare it quite easily to the one we're going to have underneath it. So we really cross zeros at negative 3 and then going all the way to 2. Okay, and then at 5, negative 5, that's where it starts. So negative 5 to negative 3, that is all greater than 0. And from negative 3 to positive 2, that's also greater than 0. But negative 2 onwards will be less than 0. So that's the way that we'll analyze that for that right there. And of course, now if we want to take then, if g prime of x is equal to the function f of x, which is on the graph, or second derivative of g, just means that we are taking the first derivative of f, right? Which again is on the graph. We just need to look at the slopes, right? So if g double prime of x is greater than 0, well, that just means we then need to look at the way things go for the slopes of the graph, right? So we have here, right, we have a negative slope there, followed by a positive slope, followed by a negative slope, and then just keep going to more negative all the way through, right? The changes, of course, are going to occur at negative 3 and 0, right? So negative 3 and at 0. From negative 5 to negative 3, that's a negative slope. 3 to 0 is a positive slope, and 0 all the way to 4 is all negative slope. Okay, very simple analysis for the first derivative of a function's graph, right? And so with that, we should be able to get through to see what that will look like on our side here. Again, we need both of these ideas to be true, that it's going to be the positive on the first derivative and the negative on the second derivative, right? So because of that, we can get the intervals here that both satisfy from negative 5 to negative 3. That's good. Okay. From 3 to 0, that's all not good. But then from 0 all the way to 2, because 2 still contains all the negatives, the second derivative that we like, and 2 ends the positives of which we like at the first derivative. So going from 0 to positive 2, that will be the other interval in which that will satisfy the conditions that we're looking for. Okay, so again, we want both positive on the first derivative but negative on the second derivative. That's what we end up with over there. Okay, and so because of that, we have then going to part C, the function h is defined by g of x over 5x. So then find h prime of 3. Okay, that's what we end up with that. Okay, so it looks like we have to do some good old, oh boy, would you imagine that, some good old quotient rule to find this derivative, right? So g of x over 5x, and that derivative is going to be something we'll have to bring up from our old memory on the quotient rule for derivatives, right? Which is the low derivative of high, which is g prime of x, less high g of x, derivative of low, which is 5, multiplied by multiplied by squared of the below. Some good old tricks and songs that I used to learn back when I was in high school to remember what that really looked like for us back then. Okay, so let's go and simplify all of that. So that's 5x times g prime of x minus 5 times g of x all over 25x squared. We can simplify some 5s there to make our lives a little bit easier. Let's straighten that out. Okay, into saying that this is just x times g prime of x minus g of x all over 5x squared. So in that case, let's go plug in for h prime of 3. So that's going to be 3 multiplied by g prime of 3 minus g of 3 all over 5 times 3 squared. Okay, very straightforward. I think we're pretty good on this because g of 3 we've already solved for before. Way back in the top of part A, we already found g of 3 as 19. So that is quite convenient for us. So we will then be able to put that together through here, giving that it's 3 and then g prime of 3. For that part right there, g prime of 3, we've already found that because g prime is equal to f, and that's going to be 0 for us there. And that's negative 3, sorry. Of positive 3 is negative 2. So we saw that already on the graph. Okay, so negative 2, and then minus g of 3, which we've solved as 19, all over 5 times 9. Time to do some simple algebra here. So it's negative 6 minus 19 over 45, which is equal to negative 25 over 45. Taking out a 5 is negative 5 over 9. Okay, quite a few things going on here, but in the end, it really does work out that we're dealing with just simply some simple algebra after utilizing the quotient rule of derivatives, which we should still remember even up till now. Okay, let's go to part D. The function p is described, so p of x is described as f of x squared minus x. Okay, find the slope of the line tangent to the graph of p at the point where x is equal to negative 1. All right, got a few things going on over here about that one. What we're dealing with the actual issue about a new function of p. Okay, so slope of the line tangent to, again, there's an actual slope of it itself. So we need to go p prime of x first, which then would involve some chain rule because we're taking derivative of a function with things inside of it. So that will be f prime of x squared minus x, then multiplied by its derivative, which is 2x minus 1. Good old chain rule coming in clutch on its own ways for us. Okay, but then we want to find the p prime of negative 1 instead. Okay, so because of that, this is just a slope yet, so it's a f prime of negative 1 squared minus a negative 1, and multiply by 2 times negative 1 minus 1. Lots of negatives that we're dealing with here, but it should be fairly simple for us to work out if we just take it one step at a time. So that's going to be a positive 1 as the result of that, plus 1 as a result of that, multiplied by a negative 2 and then minus 1, okay, which would be f prime of instead a positive 2 multiplied by negative 3. Okay, so f prime of 2, what could that turn into, right? But going back here, f prime of 2, again, that 2 line that goes all the way straight down, if you remember, already has a slope of negative 2 already from the graph that we can easily tell from all of our previous work. So we then end up with a negative 2 multiplied by negative 3, which gives us a positive 6 as a result of p prime of negative 1. Okay, pretty good. I think that looks pretty alright for us right now. So we'll hold on this and we'll get to problem number 4, and we'll see what that looks like for us, and then we'll grade it after we're done with problem number 4. Very good. Let's go flip over to the next page here. Let's see, I think we're quite dark here now because the sun is setting on my side. So let's see if I can flip that on. Maybe not. But if I just retrain the light to my face, perhaps that will make my life easier. Just hopefully I don't blind myself with my own light. Okay. Alright, I think that should be fine for now. We'll see what that looks like again. It looks like you can see everything just fine on the paper still. So that's what really matters the most right now. Okay. Very good. So, problem number 4 then. We have a table here. So let's go and write that down. So T, which is in minutes. Okay. and then v sub a of t, which is in meters per minute. Okay. We should have skipped a line, but I think we should be fine still with this divider here. So we go from 0, 2, 5, 8, and 12. Okay, now we're kind of going off here. Sure that's all set up properly. There you go. Okay, so let's draw this down here. Okay, so it goes 0, 100, 40, negative 120, and then negative 150. All right, very good. So we have all of that set up there. Okay, so it says here as context that train A runs back and forth on an east-west section of railroad track. Okay, train A's velocity measured in meters per minute is given by differentiable function v sub a of t, where t is in minutes. Okay, and then we just have the table up. Okay, very good. So that's the context that we have. We got a train and its table and how it's moving back and forth on this east and west rail. Okay, so let's go to part A here. It says here that find the average acceleration of train A over the interval 2 through t through 8. Okay, that seems pretty reasonable for us already, is that we're dealing with an average acceleration again across these different train routes here. Okay, and they give us interval 2 through 8. Average acceleration, again, given that we have velocity going to acceleration, again, the changes that we need to derive it once more with time. So if we're finding average acceleration given we only have velocity, we're going to need to go and find out exactly what that looks like through some simple average rate of change here, which is going to be the v of 8 minus v of 2 over 8 minus 2. Okay, so the simple slope of the velocity over that time interval will then give us the result that we're looking for. So v of 8 is negative 120 minus v of 2, which is 100, all over 8 minus 2. Okay, so the average acceleration then is going to be negative 220 over 6. Okay, if we were to simplify that a little bit more, I'm pretty sure the only thing is taking out here is a 2, so it's negative 110 over 3, and this can be meters per minute squared. This acceleration units, it's time squared in the denominator to make that match. Okay, very good. So we have all that together, and so we'll go ahead and see what part B is. Okay, so I wonder if they made a grammatical mistake in this. It says do the data in the table support. I think that's supposed to be does. I'm not the English teacher here, but still we'll go with what I think works best. Does the data in the table. Alright, just to show you again, this is what I'm dealing with, right? It says here in problem 4 that I just copied over, but it says here, it asks, do the data in the table. I'm pretty sure that's what he does. Again, I'm not the English teacher, but that's what I'm going to go with for now. Okay, so does the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t between 5 and 8. Okay, So it looks like we're going to do some good old intermediate value theorem, it looks like, because we're confirming a value for a function that we do have certain values for, v of t. So they're looking for v of t to be equal to negative 100 meters per minute, where t is in between 5 and 8. Right? They're asking us if we can confirm that with the table that's given. Well, let's have a look here, right? Because given that v already is a differentiable function, that does include that it's going to be a continuous function. Okay? So because of that, IVT holds up for now, given that I'm saying we can use it, given what we have so far, right? And so let's have a look here. All right. Oh, looks like I got a first chat here from Nabil Aziz, right? Yes, I think so that there were some mistakes I've made earlier this stream that we did go over. I think one of them was from a earlier mistake about in problem number 2. We can go over that again if you'd like. I do have the corrections for that. I did make some issues with converting some of the data that I was supposed to from the actual problem into the integral. But yeah, we have a whole section there that we went over it to get the proper answers. And so we'll definitely go and check, although from these parts from 3 and 4 that we're currently going over, to make sure we're on the right track on that as well. So thank you for pointing that out. We'll definitely see to it what we can do next. All right, so anyways, from 5 to 8 though, on the interval, again, we're looking to make sure that we did match the velocity that they requested is in here. So we will need to check though what the endpoints of these velocities are, so v of 5 and v of 8. Okay, so because we have that on the graph, v of 5, or that is on the table, is going to be 40 meters per minute, and v of 8 is a negative 120 meters per minute. Okay, so quite a big jump in the velocities there, but because we have a continuous function given from that table, this going from 40 to negative 120 in a continuous fashion that is, in a continuous fashion thanks to IVT, is guaranteeing us that we have to cross a negative 100 meters per minute. Again, that's a guarantee. Okay. Now, they did not ask us exactly what time that happens. We don't have the information to give them exactly when that happens, but this is going to be the correction for where this is going to go through. Yes, Nabil, them from the United States, because we're taking an advanced placement exam here. This is mainly for the United States schooling system. So all of this is going to be dealt with that schooling system, which I have taught calculus through for, I believe, close to 8 years now since I graduated. So I do have a lot of experience from that side. So we're going over a lot of old tests here. Again, this, if you want to take a look, the problems that I'm doing right now are going to be from an old exam, the 2014 free response exam from College Board, which is the United States high school exam organization, in which they post all their old exams throughout all the years. So through most of my live streams, for a lot of the things people are asking for, I normally am right now on my own time going over these problems. With the answers are also online as well, which you can follow along with. But at least for this, unless people ask me for any direct questions, this is what we are going over right now. And if you might have already seen through my YouTube channel, is that I'm currently going over specifically calculus as our first subject and any other questions that people have as we go along. So again, you're welcome to ask any questions you like, either directly through the chat or through the email that you see on the bottom left corner. And we'll be going along through this or answering any questions that are sent to us directly. Hopefully that is a bit of a good description for what we're doing here right now. Okay, so going back to it though, is that we are still having ourselves this last moment here to ensure that, again, we are guaranteeing that negative 100 meters per minute is a spot in the velocity, at least in one moment of time between 5 to 8 minutes, in which that they have asked us for. And so because of that, we will then go ahead and show that this is going to be the case for us, thanks to the intermediate value theorem, confirming that we have again, this is for a continuous function, right? And we cross from 40 meters per minute down to negative 120 meters per minute. So that velocity is indeed guaranteed for us on that interval which they asked for. Okay? So yes, it does, if you really say it in the words that they want to, it does support the conclusion. The conclusion that train A reaches the negative 100 meters per minute velocity at a time between 5 and 8, which they asked for. So this is the best way of putting that to make sure we get all the points from the test graders. Okay. So let's go to part C then for this. So it says you're at time t is equal to 2. Train A's position is 300 meters east of origin station. Okay. And then east of and the train is moving east. Okay. So it says here that we are going to write an expression. Let's see, involving an integral that gives the position of train A, okay, in meters from the origin station at time is equal to 12. Okay, but the problem still continues here. It says use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at t is equal to 12. Okay. Quite a long problem here, but nonetheless, there's 2 parts in which we need to do here. Okay. Yes, I think the lighting here, given what you stated, it's actually 5:40 p.m. So yeah, or 1700 hours around, close to 1800 hours for us. It looks like it from my camera. I think because of the lighting, but actually the sun is currently on its way down. Our sunset will be, I believe, in just another hour. So no, I know it might look like it from the screen, but I am indeed. It's actually getting close to evening for our side. Okay, but yes, we still have quite a long problem here ahead of us, and let's see if we can break this down into some easier parts for us. So, right, so we have our train at 300 meters east of the origin station, and it is as well moving east. Okay, and so we have we want to find an actual position function, and then from the position at time is equal to 12. Okay, and then from that we need to use the integral to determine where exactly this is going to be with a trapezoidal approximation. So a lot of students would be overwhelmed by the amount of things that are being asked for from this, but we just need to make sure we're sticking to the course here, and we should be well on our way from here. Okay, so it says here that we want an integral. Let's say, where is that? The integral expression here that is easily stated right there. So let's see if we can get that through. Right, so if we do integrate from the 2 time points here at t equals 2 all the way to t equals 12 is what they asked for. Let's see what that looks like. 2 to 12 for that velocity function, v of a sub t. Okay, then we should be able to then determine, right, From that, that will actually determine the position. So we can call that x of a of 12 minus x of a of 2. This is good old fundamental theorem of calculus, which will let us determine that as a result from that kind of equation. All right. So because of that, we will be getting through quite an interesting question to be able to know. No, I am not exactly in a relationship or anything like that. This is just currently something that I'm doing right now, just as part of, I think, most of where my career is headed to continue teaching math. The time is fairly normal for us here in the evening, so I don't think there's really anything else to comment about that. Thank you, though. All right, so continuing forth, though, is that we have ourselves this section here of making sure that we're trying to match exactly just the position at 12. So we're going to have to add that over, the x of sub a of 2, to the other side to make sure that we have isolated the 12-minute position over to the side that we're looking for. So from 2 to 12, v sub a of t dt. Okay. So, and oh yeah, that's right. This v sub a of 2. Yeah, that is for the. That's not very neat. Let's try that again. And that's x of a of 2 to match that. Okay, and adding that to the integral that we have. Okay, so with that, then we should be able to go ahead and put this in complete numeric terms for us, because they gave us that the position at time is equal to 2 already, is 300 meters east of the original station in which it started from. So because of that, we will get the 300 plus the integral from 2 to 12 v sub a of t dt. Okay, so that's pretty nice. And so because of that, we can go ahead and start our next point here. So this is the actual expression that we do not have to solve for right now for the position at 12 minutes for the train. Okay, and with that, we need to go with our next problem here, is that we're doing the trapezoidal sum of 3 subintervals. Okay, and we are going to approximate that as such. Okay, so now we need to find the area underneath the curve for this kind of a function. Okay, trapezoidal again is going to be the area of a trapezoid. If we remember here, is that it's going to be the actual 1/2 of the total of, actually this is written like this, so height 1 plus height 2 over 2, and we're multiplying that with the base of each of the trapezoids. Yes, Nabil, I think you find an answer, ask any of your questions you like. But I'll be continuing going through this, but yes, any of the questions you have, I'll definitely try to see what I can answer for you on. All right, but going forth from here, though, is that we then need to have the trapezoidal sum of these different types of points that were given back to us on the graph here. All right, so if those might not be able to see it, again, we're only going from 2 to 12. We're not going to include the 0 because that's not what the problem asked for. The problem says we're going from 2 to 12. So our 3 trapezoids will be going from 2 to 5, 5 to 8, and 8 to 12, right? So if you want to take note of that, again, we have 3 trapezoids. Okay, again, that's 3 to 5, or sorry, 2 to 5, that is. 2 to 5, 5 to 8, and then 8 to 12, right? Those are the 3 trapezoids here, and which have different bases. Again, that's a base of 3 for the first one, 3 on the second one, and 4 on the next one. That does make a difference, at least for the different areas for those trapezoids. Okay, so in order to find the total area here, we just need to start doing some, take the average of the 2 heights, multiply by each base, and we'll be able to see what that turns into. Okay, so with this, we have the 2 separate heights here from 2 to 5. That's 100 plus 40 all over 2. And now the base is going to be 3. Okay, and add that with the different heights here. So it's 40 minus 120 over 2 multiplied by 3. And lastly, our third trapezoid is going to be, let's see, negative 150 minus 120 over 2, and then multiplied by a 4. Okay. And Nabil asks me, what is my age? Yes, I am actually 25 years old. I graduated from university about a little bit past, so almost 2.5 years ago, for one of my local colleges with an engineering degree. So I was able to go through a lot of different math subjects, and I've been teaching it all through college as a side job to support myself through those years. So again, hopefully I have shown that I do have fair enough experience dealing with this kind of a subject, which is why I'm trying to teach it now today. So let's go ahead and run through these last bit of work here, just so that we can get an area that we can work with. So this is 140 over 2 multiplied by 3 plus, and the 40 minus 120 is negative 80 over 2 multiplied by 3. And then we have a negative 270 over 2 multiplied by 4. Okay. So we just need to continue forth with some of our next line of work here. That is going to be 70 times 3 plus a negative 40 times 3. And then adding that with, this should be a negative 270 times 2 with some simplification on the fraction bar there. Okay. And so we end up with something like 210 minus 120 and then minus 540. With the last remainder of our work here is going to be, let's see here. Let's see, that's a positive 90 there. Positive 90, and then 540, so it's negative 450 from there. Okay. And with that negative 450, again, that's going to be just the result of the integration itself, right? This was approximated negative 450. So if we want to approximate the position at t equals 12, which, why did the camera do that? Position at t equals 12, we just need to add a full 300 to this, as stated in our equation up there. So it's negative 150 meters again, or in this case, it's going to be 150 meters west of the station at the end of the 12 minutes. Okay. Now, Nabil did ask, what's on your mind to do full-time work? Well, as you might have seen through the amount of uploads that I have been doing now on my channel, is that I have been going through and making videos and these live streams as a full-time job now. Yeah, I used to work in a number of engineering/laboratory locations, but my passion really has been for teaching these last couple years, so we're trying to see how this looks out. So again, hopefully through this kind of work that I do over here, that it should gather hopefully enough attention for people to get ready to study for, at least again here in America, is that there is a big exam coming up for a lot of students in just about 1.5 months. So hopefully that answers your question about that, Nabil. But that is part C, and unfortunately I'm out of paper space here, so I actually need to flip this over to get to problem D on this problem here. It's taking a little bit longer than expected, but there's no problem for us. Alright, so let's go to part D here. It's asking here that a second train, B, travels north from origin station, okay, at time of t. The velocity of train B is given by this equation. V sub b of t is equal to negative 5t squared plus 60t plus 25. And at time of t is equal to 2, the train is 400 meters north of the station. Then it asks for us, find the rate in meters per minute at which the distance between, let's see, train A and train B is changing at t is equal to 2. All right. This one, if I remember, I think I've done this one before as well, as a bit of practice years ago. But this is quite a difficult one, but should be no problem if we go through each step at a time. Okay, so it says you that we have a train B this time. It's going north and south instead of east and west. So it's a little bit of a drawing again. We have a rail that goes east and west, if I remember my directions here. East and west. Again, this is train A. It takes those directions. But then instead we have train B that's going north and south, right? And that's train B. And so it looks like we're going to do some distance calculations at the end of this from what the question is asking for. Right? We have a velocity equation given by the problem here, in which they're going through. And then they give us the exact position at 2 minutes. It's 400 meters north of the station, right? So maybe we want to make a point there. Again, that's 400 meters for train B. Okay, so we want to find a new rate at which the distance between train A and train B is changing at t is equal to 2. Okay, so this is quite something, because in any case, going from any sort of east and west here, given that's what train A is doing, if we need to find some sort of exact distance, it looks like we need to pull our brains back to our algebra days, because it looks like we're going to do some diagonal calculations with good old Pythagorean theorem. All right. I think I remember people talking about this test back then, about how this wasn't exactly related to calculus. But in any case, though, that's what they asked for, and this is exactly what we're going to deal with right now. Okay. So let's see if we look here. Okay. Yes. Wow. Nabil notes that in his country, a 25-year-old man has a wife and children. Yes, I understand that is indeed the case with many other countries. Unfortunately, that's just not currently the way things are on my side of the world here. But at least for me, I'm still able to actually teach a lot of the younger generation about math. And I think for me, I've done a lot of science as well. So hopefully through my work here, we can continue to make some sort of connection here, and through our hard work here going through these problems for the upcoming exam. So let's have a look here. We have the actual equation that we need to note here, that if we want to find the actual diagonal distance between the two here, means that we're going to need to then describe to them what the actual distance will look like between the two. Okay, so the distance between these two different types of trains is going to be, again, it's going to be the distance c squared is equal to a squared plus b squared, right? So if you want the actual distance itself, is going to be the root of both of those functions squared. Okay. So I think for this, we're going to need to find, because we're doing the rate at which the distance is being changed here. So if we're going to do that, we're going to need to go back to the go back a step into the distance formula for part B, and then we have the distance already for part A. Okay, so because of that, we already know the velocity at part A at the 2 meters already. 2 minutes is already 100 meters per minute. Okay, and then the velocity at B of 2 minutes then is going to be, if you plug that in, 2 squared plus 60 multiplied by 2 plus 25. Okay, so negative 5 times 4 plus 120 plus 25. Okay, so we have a negative 20 plus 120 plus 25. So that means we have exactly 100 meters per minute. It looks like, oh wow, we have exactly the same on both ends here. Okay, wow, Nabil gave a very interesting comment that he thinks that I need to marry someone and have an early family, then I can teach my child who can think about me. Yes, actually, on a different note, in that sense, yeah, my older brother, he actually will have his child. She will be born in a few more months. The big joke, of course, with my family knowing that I am the big math teacher amongst my family members, that I'll have to teach her all the things that I would know and get started on that first. I think on your note, that is the closest thing that's currently going to happen. But thank you for your comment, though. We'll definitely try to see what that looks like, and hopefully in the next few months for me. Alright, so because we have these two different rates here in each direction in that sense, okay, alright, we need to see what the actual rate and the distance between the two will look like. Okay, so one thing to actually note is that for the train at A, at that 2 minute mark, is that it is actually traveling to the east. So it's actually going to be traveling closer to train B, because train B is also the train B is actually traveling north, so it's traveling away from it. So this is kind of small. So we'll try to make sure to see what this looks like here. So again, at least direction wise, again, train A is going east, and then train B is going north. All right. So what that looks like here is that because let's see here. Oh, that's right. So it's 300 meters to the east of the station. Train B is moving further away from that. The train A is moving further away from that. And then from there, train B is 400 meters north. And it also is traveling north away. Okay? So let's think about this for a second here. Okay. So we need to know the actual rate at which the distance is then changing between these two guys right there. Okay. And so because of that, we can very easily use a good old Pythagorean theorem to understand what that is going to look like for both of these. So again, if that's C that we listed out beforehand, make sure we straighten this all out. Okay. Is that these are both being added away from each other in their directions, is that it's going to be the root of 100 squared plus a 100 squared. Quite easy for us, because that means it's going to be 20,000 in the root. Okay? And that's going to be the meter squared per minute squared. But if we factor out the square root, it's going to be root 20,000 meters per minute that is changing. This between the two are changing at that time. Okay. So, yeah, I think we'll go with that for now. We might have to go back to the answers there just to make sure we're on the right track about that. Okay. I think we're pretty good for that. Okay, so let's go ahead and see. We got those two problems done, so let's swap back over to question number 3, and we can correct that together to see what that looks like. Okay. Very good. So, question number 3 from what we previously worked on here. Okay. Okay, well, looks like we've gotten something a bit off about this. I did multiply by 1/2, 5 by 4. 5 by 4.5 is 10. Why is that 19? That's supposed to be 9. Wow, I got all the work right all the way up to the last point. That's supposed to be a 9. That's a little bit embarrassing. So that's 0 to 1 because for whatever reason I slapped a 1 on there, even though my work clearly showed that it's supposed to be a 9. What a way to go, huh? All right. Although then for part B though, we get the exact interval from -5 to 3, -5 to -3, and 0 to 2. That's exactly what they wanted. So, and the reasoning showing from our work is good. So that's 2 out of 2 correct on this part. Pretty nice. Okay. And then part C ending up with, wow, okay, this is really getting me right now. Okay. A 5, 15. Well, I factored that out. So factoring that out, getting rid of that. D squared 9. Yep, that's all good there. What would be the main issue then? Oh, it's because that's supposed to be a 9. 6 minus 9 makes it not a 1/3 though. What would be the cause for this? Because -2 is correct, so I mean, no, I need to do it because they did the work a little bit differently than I did here. So that's good. This is be the 5 there, but that got factored out from my end. Because this, okay, let's take this one step at a time. Because this all is correct so far. This is exactly what they showed on the exam part there of the answer. And then we get that all factored out. I don't see a problem there. And then from that, we just need to plug in the 3's all the way through. So 3, 3, and 3, and 3 again there. So 30 and 45, 30. Oh, wait a minute. 5, 3, -2. So I just got 3, -2 left. And then the 5 was taken out. So 5, 9, 25. Hang on, so if this was instead the 9 that it's supposed to be, then 6 minus 9. Oh, okay, okay, that is 1/3. Okay. I'm getting really confused with my math now. Okay. So, although setting up this part actually is 2 points, thankfully, so I get saved by that. So 2/3, again, the actual wrong because unfortunately back on part A, which we've already corrected, was an issue. Okay. Then let's go down to part D here, which ending up with the 6 and the exact setup of P prime of X as I've shown right there is indeed all correct. So all the way down to the last answer, that's 3 out of 3 correct there. Okay, looks like I missed about 3 points, no, 2 points here, so that'll be 7 out of 9 points on this page. Okay, not the worst, just one, unfortunately, one silly mistake cascading down into another issue here. Okay, so let's have a quick look here. Okay. Yeah, well, let's see. Nabil commented once more that he's asking why I don't want to have a married relationship. Well, in any case, though, at least in my life, there hasn't been anything to come around for that yet. I would definitely like to, just that right now, in my current state, looks like there doesn't seem to be anything right now to make that happen. But, again, things move a little bit slowly, at least on our side over here. So again, mostly focusing on the type of work that I can do, because yes, this is indeed a little bit of a career shift for me first, if I'm looking to support a family in teaching math online. Alright, so let's get to problem number 4 though. That we're dealing with here, so the negative 110/3 meters per minute squared, the acceleration and conclusion using the, yep, that is correct for part 1. So that's good. Part 2, yes, we are going to be using intermediate volume theorem to prove that we are going to guarantee that -100 that they asked for way back there. So that is both mentioning intermediate volume theorem and guaranteeing that is 2 out of 2 points, which is going to be correct for us on that. Okay. Part C is going to be using the trapezoidal sum and ending up with that 150, the -150 or 150 west is indeed going to be correct. So let's make sure we get that all in there. Yep. Okay, so that -150 is correct. That way we should be going that point in west, setting up the integral again as they wanted. That's going to be another point there, and the trapezoidal sum adding up to that value will be the last points. So that's 3 out of 3 correct there. Okay. And so, at least for this, looks like we are having a bit of an issue with part D. let's see, because yes, they use that. Okay, so we're just to go derive that implicitly instead. Okay, so let's go over that again. My mind seemed to went blank there. Let's try again on that issue. Okay, because it actually wasn't meant to be that easy, at least to show for how what the change is going to be. So can you please have the camera focus? Hello. Can't even see my own paper at this stage. Okay, thank you. Very good. All right. Okay, so let's get back to problem number 4 again to make sure we're on the right track. So let's start with this again. This was actually correct for the time being. Let's snake that down there. That we have c squared is equal to a squared plus b squared, like this. Okay, and so because of that, again, this is the actual distance, but they don't want the distance, they want the rate for the distance change. Again, that's going to be meters per minute, right? This equation would only give us the meters of the actual distance between the trains. So what we're going to have to do is that we're going to have to go and take a derivative across the board, respect to time, for all of both trains, okay, for each of them. All right, which means that we're going to have to go and do good old implicit differentiation for each part of the trains here. So dA over dt for train A, and then dB over dt for that train as well. Okay, so we have all that coming together, and so we will go through these parts here and to make sure that we are matching this. So we can very easily cancel out the 2's for each of them. So we have dc over dt is equal to a dA over dt and then b dB over dt. Okay, so remember that in respect to time for these distances, this is going to be the velocity of A of that time and the velocity of B, train B, of that time as well. Okay, and again, we're still mentioning that we're doing this in respect to 2. All right. Well, Nabil is really laying on the questions here because he's asking which religion am I following, and I know this might not match because given that your name is Nabil and you're on that side of the planet, but I am indeed a Christian. My father is a minister as well, and I follow in his church. So, yeah, that is currently what I am following right now. All right. So, because of that, we're going to go and put these last things here together, so that we can make sure that we are dealing with the right part. So again, we are making sure that this part, right, the rate at which their distance is changing is what we want to follow along with right now. Okay? So let's go ahead and make sure that we are putting this together. So dc over dt is equal to a, and then let's see the actual location of train A at 2 minutes is going to be here. And that's the 100 meters. Oh no, it's not what it was. The train is 300 meters. Okay, and then the velocity of the 2 minutes is 100 meters per minute, and then adding that with the distance of train B here is going to be 400 meters, and then the rate for train B now is going to be yeah, we have to find that out, don't we? Okay, we did find out we already found that out earlier in our problem here at 100 meters per minute, and then we need to divide that by the total distance between the two. Okay, so I think with that we are getting quite close to what we need here. Yeah, so because of that we are ending up with, let's see, it was 100, no, it was 345, yes. Okay, that's pretty simple. Okay, so this C, that distance between the two, again, now we can go ahead and use Pythagorean theorem one more time because it's 300 meters again in the north direction and then 400 meters in the other direction, meaning that using simple going through our simple Pythagorean theorem is be 500 meters diagonal distance. The 3, 4, 5 triangle quite easily getting us through here. So by going through all of that, we can finally go to the correct fraction here to put this through, and we should be well on our way. So what we can very easily do actually is that because we have so many hundreds lined up here, we can remove the 100 from each of these, and we have end up with a 5 on the denominator. So that's going to be 700 meters, the meters squared per minute over the 5 meters, and we end up with exactly the 140 meters per minute, at least for the change in the distance. Okay, finally, that does match exactly what we need. Now Nabil is now asking, what's my lifetime duration? Well, again, it's gonna be, I can only give you my local time, which is going to be the 4 to 7 p.m. It's our Pacific Standard Time. So again, the west side of the United States. Again, if you want that in the 24-hour clock, that's going to be the 1600 to 1900, 1600 to 1900 time. Again, that's Pacific time, though. You have to convert that over to yours. But usually in 3-hour blocks is what I'll be going over. And whatever extra remaining time is going to be used to ask questions directly from whoever's going to send them in through the email, which we have on that bottom left corner. All right, very good. So a few other things to note there, but looks like we're good for it, though, to finish with the last 2 problems of this practice exam. Okay, so let's go to problem number 5 here. Okay, I think for these last 2, actually, I think it might be best because the amount of information that is stuffed into this, I might actually just need to go and swap over to the actual packet itself to see. You know, let's see. Do I need this thing underneath it? Okay. So let's see if we can answer it this way instead. I do believe I might need to switch pens here to make sure I don't bleed through. I wonder which one of you would do the job for me. Oh no, of course I have my pen on me. Okay. All right, very good. So let's get through these last 2, and that should really conclude it for today, though, and we'll see how well we scored. So we have this great table over here for 2 functions. It looks like we have both f prime, g, and g prime. So 2 different functions with their derivatives listed out there. Okay, and so we have the results from many different intervals going from -2 all the way to +3. Okay. And so it says here that the twice differential function f and g are derived for all real numbers of x, and they give you on that table above. Okay, so let's see if we can answer part A right on the paper here so that everyone can see that. Okay, so find the x-coordinate of each relative minimum of f only on the interval from -2 to +3, and justify the answers. Okay, so a relative minimum on f, what could that mean for us, right? So relative minimum, right, that is a very easy mathematical definition for us, meaning that we're supposed to be going from crossing from a negative into a positive, right, on the number line for the first derivative of f. Okay, and that's what it means to have a relative minimum of that graph of f. Okay, so for going from negative to positive, which ways can we do that, right? Okay, and again, the exact point on which it's 0, that's the point at which makes it from a that makes it from the cross between the 2. Okay, so if we were to go across, right, going from negative into positive, it looks like there's only one real point in which that happens, right, because a -0 to negative does not qualify for us. It has to be a negative to 0 to positive that will qualify as a guaranteed relative minimum for the function. So that point there is going to be the 1 on the x value, right? So x is equal to 1 for this, right? And the reason, of course, is that we are crossing from the negative to positive. Okay. Now, Nabil posed a very interesting question, is that if I can guess which country he's from if it's in Asia. Now, the only helpful hint I know is that I do know some people actually with the first name of Nabil, and they are from the country of Pakistan. So that will actually be my guess. If it's somewhere else, I'm giving you my best guess. All right. So if that is the actual x coordinate for that relative minimum that we're looking for, I think we're good on that. Okay. And then say explain why on part B. Explain why there must be value c for -1c to +1 such that the second derivative of c is equal to 0. Okay. So because of that, we then can see if what is going to be the case on that. So from, let's see, relative minimum on this. Okay, yes. Sorry, the value c, okay. Second derivative of c must be equal to 0. All right, this is good old mean value theorem that they're asking for, at least in our case, confirming that the second derivative of c must be equal to 0. All right. Of course, the way that we're supposed to confirm that is going with the first derivative, right, from the interval from -1 to +1, right, and we'll say that the average rate of change that is needed to confirm that with mean value theorem must be that we have the change here, so f of +1 minus f of the first derivative, -1 over 1 minus -1 should be equal to 0. But let's have a quick look here. But it looks like Nabil gave me a new hint here, saying that his real name is Tahmid Kabir Omi, if I pronounced that correct. I unfortunately have not met anyone with the name of Tahmid or Kabir. Kabir sounds a little bit more Arabic to me, but again, my guess is not very good right now on that. So, if I were to really just take a jab at it, that I wouldn't know if it's from the name of Tahmid Kabir, I would say, because no, the Kathir is the different name that I've met before. But again, I would just say from Saudi Arabia then would be my next guess, as that's still part of the actual continent of Asia. But again, I'm pretty sure you'll let me know if my guess is correct or incorrect. All right, but we can plug in for these values of f prime of +1. So getting back to our table of values here, so f prime of +1 is going to be a 0 minus an f prime of -1, which is also still 0, over a +2. Right, so from our use of mean value theorem that we should have known from our previous sessions here, is that it does match the f second derivative of c equaling 0. So again, we can guarantee that that is going to be the case for this type of problem. Okay. And the bill now lets me know that he's from Bangladesh. Okay. Yeah, I've only had one Bangladeshi friend when I was a lot younger, but his name was Saad. So, yeah, and his was Sahad, and his last name was Ahmed. So, yeah, I don't think that was really helpful, at least for me to pinpoint that location. But in any case, though, that is how we can guarantee with the mean value theorem that that would have been the case for part B. Okay, so we'll continue here. The function now that gives the function h is defined by h of x is equal to the natural log f of x. Okay, and then we want to find h prime of 3. Okay, and we just need to find exactly what that is. Okay, very good. So we're gonna need some chain rule to help us out over here, just to confirm everything that we need to know to find the h prime of 3. Right, we got to run through the derivative first with chain rule, meaning that we will use the natural log rule first, bringing the function f of x in the denominator, and then multiplying by the first derivative, okay, of that function. Now, of course, with that being the general form of the first derivative, we will then need to find the first derivative of 3 of that function h, right? Meaning that we need to go f prime of 3 on the numerator and f of 3 in the denominator. So because of that, thankfully we do have some great values already given to us from the table here. So f of 3 shown here on the table is a +7, and f prime of +3 is a 1/2 there. Okay, pretty good. So we can go ahead and start putting that through the system here, so that we have 1/2 on the numerator divided by a positive 7. And using some very easy algebra, by having that fraction of 1/2 divided by a positive 7 is 1/14. A very simple computational question that they asked for us on part C. Okay, and then we want to evaluate then at part D, the integral from -2 to positive 3 f prime of g of x multiplied by g prime of x dx. Okay, this is quite the doozy here, if only we actually understood what is happening in that integral over there, right? Even before we decide to even take a slightest look as to what is going on in the table, we need to know exactly what is happening over here in the pair of functions that is going on inside of that integral, right? What could be the main idea that's happening here, right? What you might notice is that we have a derivative of f and then the derivative of g on first on the inside and then the outside. This quite easy looks like we're dealing with some sort of chain rule of this function, right? So again, we don't have any equations. We simply have a list of table of values for this type of functions for f and g. So again, we need to figure out what is going on in this integral, right? And of course, if we only knew that the integral is the result of a certain derivative that goes through it, we can very easily run through this without even lifting a finger on the table that we have earlier. Okay. Now, Nabil, although, asks again if I am good at sports or something else except math. Yes, that is quite a good question. I do play. I do have a very big interest in American football, though. Not unfortunately not football in the FIFA sense, but much more in the American football sense. That's actually my favorite sport, as well as table tennis as well. Yeah, I do have my table still that I play against my father at times if we do have the time to do that. Those two are the main two sports I do. I don't compete really in them, but that's something that I do have a very big interest in. Thank you, Nabil, for asking that as well. But to go back to it again, we need to find a specific function that its derivative will take us back to here. And would you know it is that if we look at f of g of x as the base function for the integral, right? How do we know is that if we took, right? So in our if case, if we took that answer that we just got right there, we took that derivative in respect to x, we would line up everything thanks to chain rule into exactly what was inside of that integral, right? So again, by taking that derivative, it will be f prime of g of x multiplied by a g prime of x. Again, a one-for-one match of what was inside of that integral. And so this will be going from -2 to positive 3 as the limits of that integration. So now we're getting very close to plugging this into our table. Right, so going through here is that we have f of g of 3 subtracted by f of g of -2 using fundamental theorem of understanding how to plug in these limits into the end of the function there, right? And so now we can start using the table because now we have actual values of the function which we can put in through. Okay. Wow, Nabil says that he is the champion of badminton in his country. Yes, unfortunately, I have never really played badminton that often. I have known some people who have their own rackets and nets and shuttles and things like that, but unfortunately I have not had the chance to play very much, and nor do I even play right now. Yeah, but that's very interesting to know, Nabil, that you are actually very good at that sport. I might have to try to see what that looks like on the stage. But in any sense though, let's go ahead and plug in for the g of 3 and g of -2 that is given to us on the table here. So again, so g of a positive 3 is given to us as positive 1, and the g of -2 is given to us at -1. So let's take those down first to go through that first step in our problems here. So f of 1 is positive 3 minus f of g of -2 is -1. And then now we just need to plant these last two from the table, and that would result as the end of our definite integral right there. So f of positive 1 is going to be positive 2, and then subtract that with f of -1, which is a positive 8, which I'm starting to realize there's something that might have happened. No, nothing happened. We're all good. Okay, sorry. So my brain just had a moment there. So f of 1 was positive 2, and f of -1 is a positive 8. giving us a negative 6 as a result for that integration. Okay, those are all 4 parts to problem number 5. So let's finish this off with problem number 6 and we will correct those answers. Alright, so problem number 6, we've got quite the thing that's going on here with what we have here is this is a slope field, so we have all the different tick marks for the slopes of a function that goes across here, although we don't have an actual slope on the graph itself. So yes, quite full of information here, but we should be good enough to answer this on our own still. So it says here to consider the differential equation dy over dx is equal to 3 minus y times the cosine of x, and then let y is equal to f of x, the particular solution to that differential equation with the condition there, f of 0 is equal to 1. That's a point, which might be useful to us. And then function f is defined for all real numbers. Okay, so it says here a portion of the slope field of the differential equation is given below. Okay, and then sketch a solution curve through the point 0, 1. All right, very nice. So we have the point 0, 1 there. Again, with the slope field, we just need to follow the slopes of the line on that graph, and we'll be able to put that through here. So if you take a look a bit closer, is that we have positive slopes, and then there's a 0 slope here at that area right there, and then we go to negative. So we can quite easily follow along the lines there, something like this on that first half. And the bottom half, we just go in the reverse order. There's about a 0 slope that will happen right between there. So we need to curve that around. That point is something we have some there. And that will be one proposed solution to the slope field given there, going through that point right there. Okay. Nabil says, thanks friend for your previous time answering my questions. Goodbye and assalamu alaikum means peace upon you. Yes, I do know that Arabic greeting, at least through some of my friends. Yes, so hopefully you go have a good rest of your night over your side over there, Nabil. And hopefully you might be able to see me again on a future live stream. Thank you for all your chats, and hopefully we can see each other once more in the future. Alright, very good. So we have all of this part A completed, so let's take a look at part B. It says here that we need to write an equation for the line tangent to the solution. That's important. At part A, at the point 0, 1, use the equation to approximate f of 0.2. Okay, so line tangent to a curve, well, that's going to be a very simple equation, y equals mx plus b, where again, m is going to be, right, is going to be at the point 0, 1. So that's going to be f prime of 0, right? Okay, again, but they use the point 0, 1. That's important because we do have the derivative function up on the top, which has both y and x inside of it, right? So dy over dx is equal to the 3 minus y times the cosine of x. This is how we're going to find our slope. We just need to plug in the points 0, 1 into them. So we have 3 minus 1 times the cosine of 0, which is equal to 2 times a 1, which is a positive 2 from that derivative. Okay, so that's going to be equal to the slope of that function right there. And now we need to find, given the point that we're crossing the point 0, 1 as our tangent there. So that means we're going to have 1 is equal to 2 times 0 plus b. Okay, plugging in for x and y through our point there. And so 1 is equal to b is quite simple. So again, our full equation is equal to 2 times x plus 1 right there. That does satisfy the conditions. And so we're not done yet, though. They asked us to approximate for f of 0.2. So f of 0.2 means that we have to plug that 0.2 back inside of the equation. And so we end up with here a 0.4 plus 1, which f of 0.2 will equal to 1.4. Okay, so that is the result of our work there for part B. Okay, and our very last question here at part C is that they're asking to find y is equal to f of x, and a particular solution is 0, 1 still. All right, now this is where we put the last bits here as our kicker here at part C, given that we now have to go and integrate with dy over dx of, which is equal to 3 minus y times the cosine of x. So quite a daunting one, of course, one of the last segments for our lectures is going to be about this types of problems, about doing the separation of variables. So what this means is that we need the dy over, we need to move this over 3 minus y because we need to match with the dy's with all the y's on the side, and the dx's need to match over to the side with all the x's. All right, so we need to put that all together. So let's have a look here. So dy 3 minus y is equal to cosine of x times dx. And then from here, we will be able to integrate both sides of the equation in according to each of those variables, and we'll be able to put that all together. Okay, so thankfully we have the natural log rule for the integration of the equation on the right, but we cannot forget that we're dealing with the chain rule, meaning that we have a negative on the outside to cancel with that coefficient, and then cosine gives us positive sign, and then plus c on that side. Okay, now we need to isolate the y on itself, but we first would like to find that c. That c is quite important for us to find first before we start moving anything over. So let's go ahead and plug that in. So negative natural log of 3 minus 1 is equal to sine of 0 plus c. Remember that again, we have the point 0 comma 1 given to us from the problem. Okay, so because of that, we have the negative natural log of positive 2 is equal to 0 plus c. So it looks like c is equal to the negative natural log of 2. Quite nice. So with that, we can continue those last bits here. So negative natural log of 3 minus y is equal to the sine of x minus the natural log of 2. Then we need to go ahead and start moving everything over to isolate the y. So that will be a natural log of 3 minus y is equal to negative sine of x plus the natural log of 2 this time by flipping over the negatives. We raise everything to the power of e. So that will be 3 minus y is equal to e raised to the negative sine of x plus the natural log of 2. This will cancel out off of the exponent spot. So lastly, we're going to end up with a negative y is equal to 2 times e to the negative sine of x. Okay, and then it's in there. Oh yeah, and then we need to subtract a 3 on that side. And so lastly, y is equal to negative 2 e to the negative sine of x plus 3. And there you have it. We have our last bit of the equation there after a few lines of work, but it looks like we're all quite good on there. All right. Wow, that was quite of a doozy of a packet, but let's go ahead and finalize all of our answers here, and let's see what I end up with. Not as good as my last two ones, but still at least something that we can learn off of for all things that we did. So, problem number 5. Let's take a look at the answers, and let's see what we end up with. So, relative minimum at x is equal to 1 from the answer key. Looks like that is correct. The justification, of course, with our number line evaluation for the first derivative is indeed going to be 1 out of 1 correct there. Okay. Part B, using the mean value theorem and that subtraction of the average value, average rate of change that is, for that function is indeed all correct here, that we can guarantee that that is the case. That's 2 out of 2 correct for us. Okay. And then part C here is that H prime, again, making that proper chain rule evaluation there. Okay. And then, yeah, going for both the outside and the inside for the natural log, 2 points according to the answer key. And 1 over 14 is indeed correct. So that's 3 to 3 correct for this. Okay. And then lastly, going to part D for question number 5, is that we are using fundamental theorem of calculus to then understand that we're doing the chain rule for the f of g of x as a result of the integral. So going both ways into the plugging in between the two, that's 2 points. Unless the answer of -6 is also correct. So we are 3 out of 3 correct there for part D. So that's 9 out of 9 points for this page. Pretty nice, a good redemption from my previous problem. Okay. And then lastly, we have question number 5 here. Making sure we have the 2 curls on the top and bottom as solution curve. That is indeed just gonna be 1 point out of there. Again, making sure we pass through that point of 1, 0 is very important, and following the curves of the slope field is also the important bit there. Okay, going to part B right here is that we end up with the approximation of 1.4. That's correct. And as well, the tangent line equation ending up with a 2x plus 1 is indeed both correct. So that's 2 out of 2 correct for part B. And lastly, part C is worth 6 points. Wow, what a doozy. All right. So first off, separation of variables, we did just that. Okay. Then taking the integral of both sides. Yep, that's 2 points. All correct there. Constant of integration, making sure you have that plus C. Oh, yes. The classic joke that I've made in many of my videos is that leaving that plus C apparently will give you 3 out of 6. That would have been, right, so would be 3 out of 6 if you did not put the plus C. Again, like what I joke many times, is that my students should get a fat 0 if they do not put that plus C at the end of their indefinite integrals. Nonetheless, of course, I remember that, so put that through. Initial condition, plugging in for the 0, 1. Again, we're doing just that right there in this whole section right there of that problem. And then solving for y is our last bit. Okay, and the result is 3 minus 2e raised to the negative sign of x is indeed exactly what we get. So we're 6 out of 6 correct on that. We're very good. So we got 9 out of 9 on that as well. Okay, so let's add up and let's see what we ended up with on this whole part of the test. And we'll see here. So I think over here we can put this over here. So we have questions 1, 2, 3, 4, 5, and 6. 5 and 6 already were both 9 out of 9s. Pretty good on that. Okay. Part D I missed, I know, on that previous part. So let's go ahead and see what that looks like here, at least for the last bits. Okay. So for question number 4 is that going through here. So 1, 2, 3, and then 4. I kind of missed there. So out of 9, that's 5. 6 out of 9 there. Although I did use, let me double check here. I think I didn't partially grade question number 4. So no, okay, yeah. So I missed all 3. So that's 6 out of 9 for question number 4. 6 out of 9 over there for 6 over 4. For question number 4, question number 3, I think that was a 9 out of 9 here. Oh, the question 3 is a 7 out of 9 because I missed up something off the very beginning here. So 7 out of 9 for question number 3. For question number 2, we have here. Missed quite a bit on question number 2. So question number 2 I only got, because I messed that up, so looks like it's only 4 out of 9. Okay, that's a pretty big hit. We'll see what that turns out into. And then lastly, question number 1 here. If I remember, I did miss something off, just 1 off of that, right? Yeah, that was 8 out of 9 on question number 1. Okay, so with each of these questions being worth 9 points each, that'll be a total out of 54. And so let's see, out of all the 9, I only got 2 9s. Wow, okay. Let's see, 12, 19, 25, and another, so 25 and another 18 gives me 43. So 43 out of 54 this time of this one. Yes, I do remember this one was a little bit of a harder one. Many people complained about from this type of problem. Let's see, percentage wise, although the AP test is not a percentage based test though, but still nonetheless, if we wanted to really scrutinize on the percentage, this is one of my worst ones at 79.6% on the free response. Okay, a little bit above the 75% cutoff for most people, but this is indeed something we'd have to make sure I'm continuing to make sure we're very clear about, to make sure that we can answer all these questions properly. Okay, so because of that, we might want to go over this again in the future if we loop back around from these live streams. Let me double check here. We still have quite a few time for the rest of these, so we'll see. I think if I ever have time to loop back around, we'll have to loop back around on the 2014 exam, because this one was indeed quite the difficult one for us, but I think we are all indeed the better for it because of that. And so this indeed is a walkthrough on the 2014 AP Calculus FRQ. We had some friends come in through the chats, which is quite nice, just to keep everyone company here throughout this time. But in any case, though, we have quite a bit that we still need to get to. Again, we'll be continuing to post all of our lecture series and our YouTube shorts to garner any sort of interest for the comedy section that I'm looking to improve upon. But nonetheless, though, this should indeed conclude our third live stream for our third FRQ packet that we'll go through. And we'll definitely try to see you again on Thursday. So 2 days from now, we'll be going back out here again with the live of another packet. So again, hopefully this was helpful. The VOD will be on the YouTube page directly, and you could reach me through there. Again, the email again is at that bottom left corner right there. That email is very important, so that if anyone has any questions, you can send that through directly or through the chat just to see if we can answer them immediately. All right. So again, thank you everyone once again for tuning in. This was quite a little bit more difficult of a packet, but still something that we can improve upon. So with that, I wish you all a good night over here, as it is turning to evening on the West Coast where I'm from. And we should try to see you again for another video or the next live stream for us. You all have a good one now.